classifier with those fingerprints. Then he will basically apply the classifier to the test traffic, and the classifier will tell the attacker which site might have been retrieved. There's a number of assumptions here. I have not put any details about them on the slides. I can tell them orally in short. First assumption, the attacker knows which operating system the victim is using, which browser the victim is using, so that he can replicate the victim's traffic realistically and pretty well. That's probably not too bad assumption, because there are not so many operating systems and not so many browsers. In the worst case, the attacker tries all combinations and the right one will be there. Second assumption is definitely a harder assumption. The attacker is supposed to be able to extract single web requests, like the download of a single website from the stream of data. It has been shown that this is a hard problem, because most users are doing multiple stuff at the same time. There may be web radio in the background and all sorts of stuff. But for now, we're ignoring this problem, and we believe that the attacker will have somehow the capability to extract single page loads. Yeah, so that's that basically. Now, what does this website fingerprint look like? And keep in mind what I was talking about when I was talking about instances in the second part of this talk. We're starting with the output of a TCP dump this time. In a TCP dump, you get easy access to packet lengths, direction of flow, and timing. But what we're actually only interested in the very basic case is packet lengths. So in this case, you got them printed on the slide, and the target or the aim of the attack is now using those packet sizes, solely those packet sizes, finding out whether it's website A, B, C, or D. In order to give you a visual impression of what those fingerprints are looking like, they look like this in a histogram form. So on the x-axis, there are the packet sizes. Left-hand side is all packets sent by the client. Right-hand side, all packets received by the client. And you got the frequency in the y-axis. So obviously, this is pretty similar to the former problem with host names and such stuff. So we can use similar techniques, right? We applied two classifiers. The first one I have talked about already, multinomial naive Bayes. And the second one are famous support vector machines, basically the state-of-the-art classification engine used by machine learning people today. I cannot explain to you how support vector machines are working. Let's say they work magically. It works, definitely. There's something about hyperplanes separating instances, and no, you don't want to hear about that today. An important part of machine learning in general is feature extraction. And so far I've only talked about extracting the packet sizes, and this works not really well, at least not for Tor. For Tor, colleagues of mine actually found that you have to have other features in order to get more discriminating features. And these are direction markers and dropping acknowledgement packets. So you drop all the acknowledgement packets, and what's remaining is basically accumulated as long as the stream flows in one direction. So if you got 5 packets downloaded by the client, you sum them up, you sum the sizes up, and that's your new packet size. So you aggregate it. So order of flow is relevant now. We set up an experiment in order to evaluate this again. 775 popular sites downloaded via Tor in the real network, 20 times per site. And we evaluated it using tenfold cross-validation, which for all the guys who don't know about machine learning theory, in one sentence, it's a method to make sure that you do not choose, or that your examples or that your results are not due to randomness, but they are basically validated because you repeat the experiment 10 times with 10 different samples. So we started out in 2009 with that. And for single hop proxies like OpenSSH tunnels, OpenVPN, and so on, this works really well. Like 95% of those 775 websites could be identified. For Tor, it didn't work too well. It was like 3%, not to talk about actually. For the YAP or John Donym Anonymizer, it was not too bad, like 20%, already a risk maybe. But our colleague Andrei Panchenko, who actually graduated from his PhD recently, found some nice improvements which are more concerning. Now he is able to do it for Tor with up to 55% in the real network, for YAP up to 80%, and in the local Tor network he's up to 89% of accuracy now. So this is certainly bad because it's getting feasible now. And if you're looking at YAP, especially because I know that there are some YAP guys around here, so on the left side you see the Tor data, and those bars are basically the different classification methods. Tor is worst. The free cascade, the Dresden cascade, is slightly better, meaning slightly higher accuracy. And actually the premium cascade, which is supposed to be more secure, has an even higher accuracy, meaning bad for the user. And the private network, for reference only here, has basically the same accuracy as the premium cascade. So even though YAP uses bigger packets, 998 bytes per packet, it's performing worse than Tor regarding this attack. That's pretty bad news if you thought that packet sizes and padding helps protect your privacy. In fact, fewer packet sizes don't guarantee protection at all. If you're looking at those accumulated graphs here, you see basically all the packet sizes that occurred during the tests. You see that the free cascade, which is located only on one server, has very few packet sizes. You can count them on two hands probably. The premium cascade has a lot more packet sizes, and the real Tor network has really many packet sizes. And that's due to TCP fragmentation, basically, which is happening all the time in the Tor network because it's overloaded, so slow, different operating systems, and so on. So there's no guarantee regarding Tor's 512 byte cells. What I was talking about so far, beautiful, isn't it? Right? If you haven't been there today. What I was talking about so far was everything was under the closed world assumption, meaning the classifier was only presented websites it had been trained beforehand. So the classifier was always trained with 775 pages, and then it had to classify 775 different traffic samples. That's not really realistic, right? Because in the real world you got billions of pages, and only a very few of them are interesting. So that's why we left the closed world and put it into an open problem. And that's done by using a very few number of interesting sites, like 5. If you're like a law enforcement agency and you want to find out who is doing stuff on your network or in your country that's maybe forbidden because of religious reasons, that's a good cause for using website fingerprinting, from their point of view at least. And they would put basically a blacklist of pages with sexually explicit content on the network at the ISP level, and would try to find the people who are downloading that stuff, which is, from a religious perspective, not allowed in their network. What they would do is they would put a lot of random sites into one class, we call it the other class, in order to lure the classifier away from classifying uninteresting pages to those sexually explicit pages. So we need a basin where the classifier can basically put all the randomness of the internet into. The following experiment uses 5 interesting pages, samples uninteresting pages from the Alexa top 1 million list, and the question is, how many uninteresting pages should you use during classification to get less than 1% false positives? That's an important thing, to get only few false positives, because each and every time you get a false positive, you think someone retrieved sexually explicit content, although they didn't. And the graph looks like this. The answer to the question is you should use 2,000 uninteresting training instances in order to get a low false positive rate. And the true positive rate stays at 67%, which is still pretty bad from privacy research standpoint. So what should you do? And padding is obviously not so easy, but what's really easy to do at home, do multiple things at the same time. Use 2 tabs, use a web radio, use whatever you're doing that causes network load while you're doing stuff you would not like to see others. In experiments, this decreased rates down to at least 10%. So if you're doing that constantly, this attack is no issue for you. So that's basically all of what we would like to share with you today. And at this stage, we definitely have to thank Rolf Wendolski from Jondos, who contributed the first part, if I remember.
The JavaScript stuff.
And we definitely have to thank Andrei Panchenko, who contributed much of the fingerprinting stuff. And Lexi wanted to make a statement about IDEF. Are they hiring? I heard about that.
Yeah,
no.
Could be. Well, I think we're done. We'll
Yep.
take questions.
So, hands up if there are questions.
On? Okay. I have a question about the classifying of the sex types. What kind of features did you use for your classifier?
Packet sizes, nothing else. And direction. Yeah, packet
Yeah.
sizes and direction. No content whatsoever. So you need to have a list. You need to have the list of sex pages you're interested in as attacker. So no image recognition stuff.
Hello. Test data? Is it possible to download it?
Excuse me?
He's asking about test data. So you want to download test data, traffic data, basically. I can answer for myself that I have put on my website at University of Regensburg 2 gigabytes worth of traffic logs. They're old. They're from 2008. I'm not sure whether Andrei is releasing his data. Probably.
I don't know.
We should ask him, or you could contact us.
Send us a mail and we'll see what we can do.
I have a question about the header order. How accurate is the header order?
Excuse me? Could you?
Speak up, please.
Yes, sorry. The order of headers in the browser.
Yeah.
The browser sent. How high is the false positive rate on fingerprinting with using that?
Well, the big point is measuring false positive rate. If you assume that we measure false positive rates by customer complaints, then up to now it's 0.
Okay. Thank you.
I want to know how static the fingerprint of a website you're making is, because I'm thinking about pages like 4chan and things. They change quickly enough that a text doesn't seem viable for pages like that. Just wanted to know if there's mitigation of that or stuff.
Yep, so you're asking about whether it makes a difference, whether the page content changes, whether that makes a difference. First, in our experiments, the rates didn't decline much if the offset between training and test were like 2 weeks. So that makes almost no difference. And it's easy to explain because it doesn't make a difference if the text, if the contents change. It makes only a difference if the structure changes. So 4chan especially might be tricky due to its nature, but news pages, sexually explicit pages probably work pretty well.
But then again, nothing stops you from retraining your classifiers every half an hour.
Question from IRC. Is it difficult to fingerprint websites which change very frequently?
I think we got that already covered just right now.
Internet never disappoints.
How does caching affect the fingerprinting?
Sorry, how does what?
Caching.
Did you get it?
Caching?
Browser caching.
Caching. Oh yeah. I did actually experiment on that, not with Tor, but with OpenSSH, and it's decreasing rates from 98 to 92 or something like that.